Hello everyone. So this is the first video lecture in this series, and we'll start off with what vectors are and how they're relevant to embedding functions and how embedding functions are needed in machine learning problems. So let's start off with what vectors are. So a vector is basically a point representation in any n-dimensional space. So here we have R2, a space in 2 dimensions, a real space in 2 dimensions. So we have the axes x and y. We can represent a point, say A, with coordinates a, b. So this is a vector in R2. So A has a distance along the x-axis from the origin, which is a units, and has a distance b units along the y-axis from the origin. So the same rule holds for 3 dimensions as well. So we can have a 3-dimensional space x, y, z, R3. Here we can have a vector, say k, with coordinates a, b, c. So here's a vector in R3. So the rules that hold for vectors, the mathematical rules that hold for vectors in R2, they hold for R3, and they keep on going till Rn. We can extend the dimensions as much as we want depending on the problem. It doesn't matter if we can visualize them or not, but the mathematics would hold. So this is something which we exploit in machine learning quite a lot, because in machine learning the problems go far beyond 1000+ dimensions, and the human mind cannot imagine or visualize more than 3 dimensions. Now that we know what vectors are, let's come to how they're relevant to embeddings, or in general what embeddings are and why they might be required. So let us formulate a problem statement for ourselves, which is like so. So classify humans and dogs from image input, right? So we can think of humans and dogs as 2 different classes or 2 different sets, right? So humans can be, there are different types of humans, different instances, right? So humans can be fat, humans can be thin, humans can be old, humans can be male, female, anything. Similarly for dogs also, we have attributes like the breed, etc., that distinguish them. So we have many different types of dogs. Now, based on an image, say I give you an image of a person and a dog. So if I tell you to distinguish between the two, it would be very easy for you to do so. But if I were to ask you how did you do it, what was the mathematical function that operated inside your brain to figure out which is which, it would be very difficult for you to say that, right? So the problem is basically asking the same thing, like, is there a mathematical function which can operate on this contextual input? So contextual input is a very important term here. So contextual input means input which is non-numerical in nature, right? Non-numerical representation of data. So based on this contextual input, is there a mathematical function that can, in this case we have to classify, that can give you a Boolean output maybe. So a Boolean output as in, like, if you are giving a human input, then you expect the output to be true, or if you are giving a dog input, then the output should be false, right? So for the dog we are expecting a false, for the human we are expecting true, right? So this is what the problem statement is asking. But the issue is that we cannot train a model on contextual input. It is virtually impossible. So we need a middle layer here, right? So what would the middle layer be? Here we need something which will extract the features or attributes from these inputs and give a vector representation, which would be the input to the model, right? So this middle layer here is called the embedding function. Embedding function, or the embedding model, and this F here is the classification model, right? So right now we will concern ourselves primarily with the embedding model here, as this is what we are interested in at the moment. So how do we extract numerical data from contextual input? So for this we need to understand what feature representation is. Like this human, I mean, all humans and dogs have some attributes, right, that can be numerically represented. For one attribute can be number of tails, and another attribute can be number of legs, for example. So if we like tabulate humans against dogs, so human against dog, if we tabulate them, so human would have 0 tails, and a human would have 2 legs, a dog would have 1 tail, and it would have 4 legs, right? So basically, based on these two attributes here, we are able to numerically extract some data from these contextual inputs, right? So these images can be transformed into some numerical representation. So suppose this is the definition of our embedding model. Then if we give human input to the embedding model, or the extraction model, you can say, you'll get, say, for the human, we'll get nt is 0 and nl is 2. And if we give it a dog input, then it will give 1, 4. So 1 is the number of tails, 4 is the number of legs, right? So we have been able to extract numerical information, non-contextual information from contextual data using the embedding model. Now this is the significance of the embedding model, basically. Although here we define the rules ourselves, but in most problems the embedding models are trained via gradient descent. So they are initialized via random values, and then they basically back propagate from the losses, and then the weights are adjusted. So I mean, the gist of the embedding function here is that we take non-contextual input and transform them into contextual output, which can be fed to a model that will basically perform the objective task, right? So I mean, if we represent this projection, it would look like this, right? So on the x-axis, if we show the number of tails, and on the right axis, on the z-axis, on the y-axis, if we show the number of legs. So humans would be somewhere in here, right? So humans have 2 legs and 0 tails. So humans would fall somewhere in here. So most of the humans would fall within this cluster, right? And dogs, most of the dogs have 4 legs and 1 tail. So 4 is here, and number of tails is 1. So most of the dogs would fall within this cluster, right? So we can distinguish very easily now. Now suppose if we were asked to generate a curve separating these two clusters, it would be very easy for us to do so. We could always do it through a line, right? A line would be the simplest curve separating these two clusters. And the fact is that this line would be the objective model, which we are representing here. This would be the objective model, right? So the embedding function basically takes contextual input, it transforms it into some vector output, numerical representation, which is then fed to the objective model, which will finally give the output to the problem. Now here one more thing is very important, that is the choice of the features that we choose to represent to represent the contextual input. So here we chose the features to be number of tails and the number of legs, but suppose if we chose eye colors, then there would be a lot of overlap. So it is important that the features are chosen wisely. In this case, again, we are choosing features in a handcrafted fashion, but in most machine learning problems, features are chosen randomly, and through back propagation, they are the weights of these features are adjusted to fit the problem. It is intuitive to think of features extracted from contextual input like images, but what about contextual input like words? For example, the word bat, it can mean a sports object, sports utility, or a flying mammal, right? So how do we represent these kind of words? Words in terms of words or vocabulary in terms of some numerical representation. What kind of features do we extract from them? Because the other words in their surroundings will influence their meaning, right? For this, we need certain tools in neural networks. They are called transformers and transformer-based embedding models. which we will discuss in the next video. But I just wanted the gist of what embedding and what the objective function is to be clear here. So I hope this clarifies your doubts. Thank you so much.